Diving even deeper into our activity, remember my comment in chemistry that whenever we have a reaction occurring, we talked about this in Chemistry 5, whenever we have a reaction occurring, we're talking about an exchange, a transaction of electrons. So when electrons move around, they break and reform and alter bond structure. Electrons are always moving around, though. Sometimes they move into very unstable, unfavorable configurations, and other times, most of the time, they're going to be in their most stable configuration. If I'm comparing the configurations of benzene rings, for example, there's two different what we call resonance structures. You can see that they are completely identical. There's no difference between this and this benzene ring. The electrons can move around, and they do. And because they're totally equivalent, and they'll constantly be moving around like that, we can actually just draw those as this little circle in the middle. We call these electrons delocalized. Okay? These electrons are delocalized in that they're not in a specific bond configuration at any definable period of time. Okay? The carboxyl group can do the exact same thing. When the carboxyl group has been deprotonated, you have this O- and this C double bonded to O, this carbonyl. And those look pretty different, but it turns out that there really is no difference between the two. I can get the bond to drop down, so I can get those electrons to drop down. Pull my pointer out. I can get these electrons to drop down, form a double bond here, and then this bond, to keep the carbon atom from having 5 bonds, will pop up. So there's no difference between these two carboxylic acid or carboxylate ions. And so we can call these also being delocalized. The electrons aren't really in any one place. Totally equivalent. Now, when this becomes protonated, so when this turns into an OH, then this one definitely will become a carbonyl. But as long as it's deprotonated, it'll be delocalized like this. And delocalization, or spreading out of electrons, actually helps increase the stability of molecules, okay? Particularly of certain types of bonds, or in this case, charges. And we're going to talk more about that in the second organic chemistry lecture. Okay. To add to this, again, it's important to recognize that a lot of different resonance structures are possible. For example, these two are both possible, but the one on the right is less stable. It prefers to be the one on the left, and it's going to spend more time that way. But the fact that it is capable of being the one on the right, even though it's more stable, often helps drive certain reactions. The more stable certain resonance structures are, sometimes the easier it is and the faster a particular reaction will occur. So now we can actually talk about reactions proper, right? In reactions, you have an exchange of electrons. Some nucleophile attacks some electrophile. Nucleophiles are nucleus-loving. They have a very high electron density. So nucleophiles are generally negatively charged or have a partial negative charge. Or they can have pi bonds. So alkenes are considered nucleophiles. Electrophiles are electron-loving, hence the name electrophile. They want electrons, and the reason they want electrons is either because they're positively charged or because they have a partial positive charge, delta positive versus delta minus. And generally speaking, nucleophiles will attack electrophiles. There are certain instances when we call a reaction electrophilic substitution or electrophilic attack, and the distinction between those is not going to be important for the MCAT, suffice to say, it's largely a technicality for purposes of the exam. Because ultimately, what's happening in either version, in either form, is electrons are doing the job of some reaction. Electrons are moving from one compound to another, from one atom to another, and breaking and reforming a bond. So typically we'll see this in the form of a nucleophile going after an electrophile. Not always. Sometimes it's the electrophile that comes in and forces the nucleophile to give it electrons. We'll see that particularly where we have pi bond systems. Electrophile will come in and take one of those pi bonds, one of those electrons, but for purposes of the exam, that distinction is not important. Common nucleophiles in the order correlated to the stability of the species in solution. Okay? These alkoxide ions, hydroxide ions, are not very stable in solution. They really want to go after an electrophile. But something like iodine ion is very stable. It's a pretty bad nucleophile. Chloride, also relatively bad nucleophile. These trends are actually much deeper, or can go much deeper, than what you need to know for the exam. As long as you understand that there's a correlation between the stability of the base and the nucleophilicity, so the less stable it is, the more willing it is to attack onto an electrophile, you'll be able to predict everything you'll need to predict for the exam. Electrophiles, common electrophiles are, remember, either positively charged, so protons, carbocations, which we'll see in a moment, the hydrogen of the hydrogen halide, the alkyl group of the alkyl halide, the carbon of the carbonyl. These are common electrophiles. And you need to be able to identify nucleophiles and electrophiles because you'll need to be able to have a basic understanding of how reactions occur and why certain reactions will occur. When we have certain types of reactions, certain substitution reactions, we will have a nucleophile come in this case, this nucleophile, the hydroxide nucleophile, is a better nucleophile than bromide. It'll come in, it'll attack the electrophile, remember the alkyl group of the alkyl halide, and we'll have a leaving group. The leaving group is the group that comes off. You don't always get a leaving group when you have nucleophilic attack. Sometimes you can have nucleophilic addition reactions, but other times you do. You have a leaving group, or you have usually a substitution reaction when you have a good leaving group. If you have really bad leaving groups, you'll generally just get nucleophilic addition reactions. You won't really do a substitution because there's no good leaving group to come off. So here we see a list of leaving group E's. Iodine, not a very good, the iodide ion is not a very good nucleophile. So it's a pretty good leaving group. It'll come off, it's pretty stable. Okay. Now, let's quickly recap some of our important concepts from general chemistry. You can see it's going to come back in organic chemistry. Here I have these three acids, and you can see my three values for Ka. And my question to you is, which of these acids is the strongest? Based only on the information here, it is sufficient. Which acid is the strongest? The answer is Hi. How do I know? Because the value of Ka, 10 to the 10, is bigger than 10 to the 8. The value of Ka is larger. And I know that the Ka equation is H plus. In this case, it would be iodine minus over Hi. Okay. The larger the Ka, the bigger this numerator. So Hi has a larger numerator, which means it has a bigger concentration of protons, and therefore it is a stronger acid. And that should make sense because we know that iodide is a more stable conjugate base. It's more stable in solution, so it doesn't really want to go back and attack onto the proton. It's fine in solution as an ion. Okay? So, HI is going to be the strongest acid because it's got the most stable conjugate base. And that's consistent with it having a good leaving group, having a weak nucleophile. Carbocations are also really good electrophiles. These are positively charged carbon atoms, so they only have 3 bonds. And we should know our nomenclature here. We have methyl carbocations, primary, secondary, tertiary. This all depends on the number of carbon atoms that the carbocation is bonded to. So if it's only bonded to 1 carbon atom, it's a primary. 2 carbon atoms, it's a secondary. 3 carbon atoms, it's a tertiary carbocation. So because they're positively charged, they're often the subjects of nucleophilic attack. Nucleophiles, being electron-rich, will go after them. And you form these as intermediates in a lot of reactions. Another property of carbocations, which is interesting, is their ability to rearrange themselves. Tertiary carbocations are more stable than secondary carbocations, and secondary carbocations are more stable than primary carbocations. So carbocations will actually, in certain circumstances, rearrange themselves such that they can become more stable. So here's an example of a compound which has this leaving group, this hydroxide, which comes off as a leaving group. It forms this carbocation. Okay? What kind of carbocation is this? Think about that for a second. Okay? This carbocation is bonded to 1, 2 carbon atoms. So this is a secondary carbocation. This hydrogen atom, because it's available here, can be switched over. And now I have a tertiary carbocation. Note this isn't always possible. You have to have an adjacent carbon atom or a hydrogen atom that is available to donate a hydrogen bond. I shouldn't really call it hydrogen bond, but a hydrogen atom. And in this case, it forms from a secondary to a tertiary carbocation. Tertiary carbocations are more stable.
For most students, and maybe you too, the CARS is the hardest section on the MCAT. It may feel like it's one of the few remaining obstacles between you and the medical school of your dreams. But as you try to prepare for the CARS, you find there is a never-ending stream of conflicting tips, strategies, and plans, none of which seem to actually help or show any results. If you feel frustrated, overwhelmed, or lost when it comes to the CARS, if you're looking for a CARS expert who has helped thousands of students achieve their MCAT CARS goals, then you've found your solution. Testing Solutions MCAT CARS Bootcamp. Founded by Nick Zahner, a current medical student at Stanford with a master's degree in philosophy of religion from Harvard, Testing Solutions' approach to the CARS is revolutionary. Testing Solutions CARS Bootcamp provides day-by-day, step-by-step instruction that teaches you the techniques that produce ultra-high MCAT CARS scores. Instead of wasting your time with the needlessly complex filler that other companies try to sell you, Testing Solutions' approach to the CARS is based on the principle of minimum effective dosage. There's no wasted time, just the minimum amount of effort that is required to get you the results you want. With over 500 4.5-star reviews on Amazon, Testing Solutions CARS Bootcamp is the most trusted, proven, and effective CARS course available on the market today. You will have access to Testing Solutions' 180 meticulously designed CARS passages, the largest CARS practice library offered by any MCAT prep company in the country. Our passages are regularly rated by users on Amazon, Reddit, and SDN as the most accurate non-AAMC CARS practice passages available, consistently rated higher than Exam Crackers, the Princeton Review, Kaplan, and Next Step. Unlike some companies who prey on pre-medical student fears by charging outrageous amounts of money for their mediocre at best practice materials and courses, Testing Solutions will always charge a fair price for an amazing product. Because after all, we're not like the other test prep companies. We're aspiring doctors just like you, only a little further down the path. Let us help you do what we've already done. If you're not happy with your CARS Bootcamp for any reason, we offer a 100% money-back guarantee, no questions asked. You've got nothing to lose and the CARS score of your dreams to gain. Don't be one of the people who write us each week saying they wish they had found our MCAT CARS Bootcamp sooner. You don't have to struggle with the CARS any longer. Sign up and get started today.